Now that we've spent some time getting familiar with exponential and logarithmic functions, we're ready to take a look at some applications where we can use exponential and logs to help us solve real-world problems. We're going to start with something from chemistry called a half-life. What a half-life is the amount of time needed for half of something to decay away. A classic example of this is carbon dating. We can look at something that's really old because carbon, half of it decays away every so many thousand years, and so we can use that to estimate how old an old artifact is. But our bodies also operate with half-lives. If you take some medicine, your kidneys and liver will filter it out of the blood, and so that's why you need to take another dose of Tylenol every 6 to 8 hours, because it's got a half-life as it decays away. The formula we're going to use for half-life is F equals P e to the RT, where F is the final amount, P is the principal or starting amount, R is the decay rate, and I'll give you a hint, we need to find this first. And T is the time of decay. So for example, if I've got some chlorine 36 in the body, it has a half-life, a biological half-life, of 10 days. Means after 10 days, half of it's been washed out of the system. How much of 30 micrograms remain after a week, 7 days? Well, the first thing we're going to do is separate this into two problems. First, there's the half-life of 10 days, and then there's the 30 micrograms after 7 days. We want to keep those two problems separate. First, finding the decay rate, we're going to say the final amount is half, because we're talking about a half-life, is equal to the starting amount, which is 1 whole, of e to the decay rate times the amount of time it took us to get to that half-life. So because we have a half-life, we're plugging in half, doing the first problem. Well, I'm going to simplify this to 1/2 equals 1 times anything is just that stuff, and we usually put the number out front. And we know we can get stuff out of an exponent. We can solve by taking a log of both sides. I'm going to use a natural log because we already have a base of e, and the natural log and the base e will undo each other, just leaving 10r. And so we have the natural log of 1/2, or 0.5, is equal to 10r. And I can divide both sides by 10 to get r is equal to, do that on my calculator, I'll get negative 0.06931. So we've solved the first problem. The second problem is I've got 30 micrograms, and I want to know how much is left after 7 days. So going back to my original formula, F, the final amount, is equal to the principal or starting amount, which is 30 micrograms, e to the r, which I now know is negative 0.06931, times the time, which is 7 days. I just need to put this in the calculator just like it looks. Depending on your calculator, you might need an extra set of parentheses around the exponent. And when I do, I find the final amount, starting with 30 micrograms. After 7 days, there's now 19.26 micrograms left in the body. Very similar to half-life is another type of problem that comes out of the sciences, which is that of doubling time. If half-life is the amount of time it takes us to have half of the stuff left, doubling time is the time it takes for a population or the stuff to double in size. And because it's closely related, you're going to see the same formula. You're going to see F equals PE to the RT. And it all means the same thing. F is the final amount, P is the principal or starting amount, R is the growth rate, and T is the amount of time. Again, we're going to see the hint, though, that we want to find R first because the problem is going to have two parts to it, just like the problem had two parts last time. For example, college tuition doubles about every 11 years. So if it costs $40,000 for a freshman now, what will it be in 4 years when this freshman graduates? Well, again, we've got two problems here. It looks like one problem, but there's really two. We know it doubles every 11 years. That's one problem. And we know it costs $40,000, and we want to know how that's going to grow in the next 4 years. Let's keep those problems separate as we solve. First for R, and then answer the question. For the final amount, if we're talking about the doubling every 11 years, the final amount is going to be 2, showing that it's doubled. The principal starting amount is 1, because you always start with 1. E to the R, we don't know that R, that's what we're looking for, but we know the time is 11 years. Rewriting this, 1 times anything is just that stuff, and so we know 2 is equal to E to the 11R. To get that stuff out of the exponent, we know we can take the log of both sides, and we're going to choose a natural log because we have a base of E, and that simplifies quite nicely, giving us the natural log of 2 equals 11R. I can divide both sides by 11, and I now know that R is the natural log of 2 over 11. Again, as I put it in my calculator, I'm careful to close parentheses, and I find out that R, my growth rate, is 0.06301. Now I'm ready to go to the next question. If it costs $4,000 now, what will it be in 4 years? We're looking for the future value. If it's $40,000 now, times E to the R, which is negative 0.06301, times time, which is the 11 years. Again, be careful how you put in the calculator. Your calculator might require an extra set of parentheses around the exponent. But the future value of that tuition, when I put this in my calculator, is $51,465.90. Both the doubling time and half-life problems use a very similar formula and process in order to solve. And that formula should look familiar to you because we've actually used it before. We used it before in continuous interest. And we can use logs and exponents to help us find the time it takes to reach our goal. Again, we're going to use that same formula, F equals PE to the RT. This time F is the future value, P is the present value, R is the interest rate, and T is the time. but we've seen these variables before, so we can answer questions like how long to invest $800 at 7% interest, compounded continuously. To grow to $1,000. Well, this is nice because they've already told us our rate of growth is 7% or 0.07. So we don't have to go back and find it like we did in the previous two problems with half-life and doubling time. So really all we need to do here is plug it into our formula and solve the resulting formula. F, the future value, is going to be $1,000. P, the principal starting value, present value, is $800. Times e to the r, which we said is 0.07, times time, and we want to solve for that time. Recall from solving problems with exponentials, before we can do any log stuff, we have to get the exponent part alone, which means we have to get rid of that 800. Right now it's 800 times the e, so we'll divide both sides by 800. 1,000 divided by 800 reduces to 5/4 equals e to the 0.07t. Now that the exponent part is alone, we can take a log of both sides. Again, because we have a base e, we're going to do a natural log because those will be inverses of each other, leaving just 0.07t on the right and the natural log of 5/4 on the left. We can get our t alone by dividing by 0.07. And t is equal to the natural log of 5/4 divided by 0.07. Being careful with parentheses as I type that into my calculator, the amount of time it's going to take my $800 to grow to 1,000 is about 3.19 years. Well, if we can use this process to find out how long it takes to reach a goal with continuous interest, it might beg the question of how long would it take to reach our goal with regular compounded interest. So let's change the problem slightly. Let's look at compound interest. Compound interest, again, we're going to look at the time it takes to reach our goal. But this time we're going to use the compound interest formula, which we saw in a previous video, that the future value is equal to the present value times 1 plus the interest rate divided by the number of compounds times the number of compounds in a year times t as an exponent. So we can answer the same question, how long to invest $800 at 7% compounded quarterly to grow to $1,000. So now instead of continuous interest, we've got quarterly compounding interest. How does that change things? Well, the future value is still $1,000. The present value is still $800 times 1 plus the interest rate, which is always written as a decimal, 0.07, divided by the number of compounds in a year. Quarterly means that it compounds 4 times per year, every quarter. So we'll divide by 4, raised to the 4 times t power. I'm going to simplify the problem a bit by doing the parentheses here. So we've got 1,000 equals 800 times 1 point, when I put this in my calculator, 0.0175 to the 4t. Again, before I do any log stuff, the exponent part needs to be alone. So we've got to get rid of 800 times by dividing both sides by 800. And that reduces to 5/4 equals 1.0175 to the 4t. And now we can get that out of the exponent by taking the log of both sides. Well, this one's a little inconvenient because it does not have the base of e. So it's going to be a little bit more work. I'm just going to do a regular log base 10 because we don't have a button on our calculator for the base 1075. So that's going to give us the log of 5/4 equals, and whenever we have an exponent inside of a log, it can come out front. So 4t times the log of 1.0175. We want to get the t alone, so we'll divide both sides by 4 log of 1.0175. So the 4's are gone, the logs are gone, and we're just left with t equals. And I'm going to be very careful as I put this in my calculator because there's multiple things happening in the denominator. I have to put an extra set of parentheses around the denominator. Also make sure I close the parentheses on my logs, and what I find is the time is 3.22 years, basically 3¼ years because it's compounded quarterly. It will take for that $800 to grow to 1,000. I want to do one more example of how we can use logs and exponents, and it's going to be kind of a variation of that PE to the RT formula that we saw before. And that's going to be what's called Newton's law of cooling. Newton's law of cooling tells us the speed that the temperature of something, of an item, changes to match its surroundings. The classic example of this is you take the turkey out of the oven and it's really hot, 425 degrees or whatever, and then it will slowly cool down over time as it sits on the counter in the cool air. The formula for this is T with a subscript of F is equal to A times e to the kT power plus the temperature of the space around it. So T with a little f, that's the final temperature of the thing, whatever we're talking about. T sub s is the temperature of the space around the thing. Then A and K we need to find. A first, then K. And they're going to be constants that really depend on whatever thing we're talking about heating up or cooling down. And then, of course, the lowercase t we've seen before as time. So, if I have some water at 40 degrees Fahrenheit in a 70-degree Fahrenheit room, an hour later, it will increase to 45 degrees because that water is going to warm up to room temperature. I want to know how long to reach 60 degrees in this room. Well, the first thing we know is that the temperature of the space around it is 70 degrees. So I would start by writing my formula. The temperature at the end is equal to AE to the KT plus the temperature around it, which is 70 degrees. First thing we're going to do then is to figure out what A is. And the easy way to figure out what A is we say if time is 0, what is the final temperature? What is the temperature at 0 time passed? Well, it started at 40 degrees. So 40 degrees is equal to A times E to the 0 times K, because time is 0, plus 70. What's nice about this is 0 times K is 0, and E to the 0, anything to the 0 power is 1. And 1 times A is just A. So it really just leaves us with the A. So 40 is A plus 70. Subtract 70 from both sides, and negative 30 is equal to A. Okay, that's kind of nice because now my formula is the final temperature is negative 30 e to the kt plus 70. We're starting to fill in the pieces. To figure out what the K is then, we're told an hour later the temperature was 45 degrees. So at 1 hour, the final temperature is 45 degrees. So if I put 45 in there, equals negative 30 e to the k times 1, because it's 1 hour, plus 70. This is an equation we can solve by trying to get the exponent part alone. First, we'll subtract 70 from both sides. Gives us negative 25 equals negative 30 e to the k. Divide both sides by negative 30. And e to the k is equal to, dividing both by negative 5 gives us 5/6. Now that the exponent part is alone, I can take the natural log of both sides. So the natural log of 5/6 is equal to, natural log and e undo each other, k. Put that in my calculator, the natural log of 5/6 is negative 0.1823. So now my formula is starting to take shape a little bit better. The final temperature is equal to negative 30 e to the negative 0.1823 times the time plus 70. We're now finally ready to ask how long until the final temperature is 60 degrees. We want that final temperature to be 60 degrees equals negative 30 e to the negative 0.1823 t plus 70. And we just have to solve this equation in order to answer our question. Subtract 70 from both sides. Negative 10 equals negative 30 e to the negative 0.1823 t. Divide by negative 30. That's going to be a positive 1/3 equals e to the negative 0.1823 times t. To get rid of the e, we take the natural log of both sides. So we have the natural log of 1/3 equals negative 0.1823 times time. Get time alone by dividing by negative 0.1823. And when we do, again being careful with parentheses on my calculator, time is equal to about 6.02 hours. So after 6 hours, this glass of water has warmed up from 40 degrees to 60 degrees in the 70-degree room. All right, it's your turn to practice some of these applications, these models of exponentials and logarithms in the real world. Good luck on the assignment, and we'll see you in the next video.